Light from the sun reached the outer system and spread across a quiet frame of sky. The detectors watching that frame expected the standard pattern: background galaxies, local asteroids shifting in predictable arcs. Instead, a single point shifted against expectation. On the raw images, it was almost nothing. A faint source, near the limit of the survey's reach. Across sequential exposures, the point translated not with the slow, looping motion of a bound object, but with the straightened path of something simply passing through. Initial orbit solutions marked it as unbound. A new interstellar visitor, the third ever recorded. That alone would have been enough. A new trajectory, a new velocity vector, a new path through the geometry of the solar system. But the spectrum did not match the orbit. Follow-up instruments separated its light into wavelengths and measured the distribution with precision. The absorption features did not align with the minerals that built the planets, or with the ices and dust that shaped comets and asteroids in the protoplanetary disk. Instead, the pattern resembled solids formed in environments older than the sun itself, older than the local cloud from which the solar system condensed. The numbers converged. The mineral composition implied formation more than 4.7 billion years ago. Not just older than Earth, older than the star that illuminated it now. Around it, the solar system functioned as usual. Planets moved in their ellipses. Dust trailed in resonant bands. The sun burned at its calculated luminosity. Against this ordered system, a dark, compact body slipped through space, carrying a composition record that preceded all of it. A thin vector crossed the field, connecting a deep past to the present gravitational well. An object older than the sun was now cutting through the planetary system that did not yet exist when it formed. The discovery sequence began with routine survey cadence. Wide-field telescopes stepped through programmed tiles of the sky. Each exposure captured a deep field, then the instruments moved on. When automated software compared images, one faint source failed to fit the expected motion catalog. Its track did not match any known asteroid family. The apparent speed and direction suggested a trajectory not anchored to the sun. Flagged as a candidate, the object was passed to follow-up networks. Mid-sized observatories turned toward its coordinates. Larger telescopes narrowed the beam. Measurement teams coordinated across longitudes to build continuous coverage. Time-stamped images showed the point of light sliding along a path that could not be closed into an ellipse by adjusting orbital parameters. Only a hyperbolic solution produced residuals within acceptable limits. The unbound nature was confirmed. The third interstellar object, designated as 3iATLAS, entered the record. Spectrographs were brought online. Prisms and gratings split its faint light into discrete wavelength bins. Integration times were extended to raise signal above noise. Frames were stacked. Calibration lamps set the wavelength scale. The resulting spectrum departed from expectations. There were absorption bands where ordinary silicate bodies showed none. There were missing bands where standard cometary volatiles should have appeared. The continuum slope and line depths pointed to minerals that formed under pressure and temperature histories inconsistent with the protoplanetary disk that birthed the sun. Independent teams repeated the measurements. Ground-based observatories at different latitudes. Space-based platforms with no atmospheric interference. Results converged within error margins. Astrometric Station, a compact interstellar body now moving through the solar system, carried a solid-state record of conditions older than the sun. Once the object's status was secured, the observing campaign shifted from detection to characterization. The first priority was the balance between absorbed sunlight and emitted thermal radiation. Internet measured its brightness at visible wavelengths and in the infrared, tracking how quickly the surface heated as it approached the sun, and how quickly it cooled as it moved away. The derived radiative balance indicated a surface that absorbed most incident light and re-emitted energy slowly, consistent with a dark, refractory mix of minerals and metals rather than bright ices, much like a fragment of industrial furnace brick placed near a heat source, soaking energy before releasing it over time. The motion profile was then analyzed at the level of changing velocity, not just position. Successive astrometric measurements allowed calculation of the rate of change of its velocity vector under the sun's gravity. Within measurement precision, the derivative motion matched pure gravitational acceleration along a hyperbolic path, with no detectable non-gravitational thrust from outgassing. It behaved like a dense test mass in a vacuum chamber dropped through a controlled field. Its fall described almost exactly by the equations, without measurable perturbation from internal forces. Surfaces scatter light in characteristic ways, and 3iATLAS was no exception. By measuring brightness at different phase angles, as the geometry between the sun, the object, and the telescopes changed, teams derived the reflectance behavior of its outer layers. The phase curve was unusually flat, indicating a surface that maintained similar brightness over a wide range of viewing angles, consistent with a rough, microfaceted texture created by countless small fractures, similar to shining a lamp on a densely pitted metal casting that looks nearly as dim from many directions. Longer baselines revealed that the path of the object did not trace a perfectly smooth mathematical curve when plotted at extremely high resolution. Tiny deviations appeared as measurement precision improved, each within error margins but collectively forming a pattern worth examining. When the apparent path was compared against a pure two-body solution, a slight, systematic offset emerged, suggesting the influence of distant, massive bodies and the distributed pull of the galactic tide on its incoming and outgoing legs. Like observing a puck sliding across a near-frictionless surface while a faint sideways tug from a distant magnet shifts its track by millimeters over meters. Photometry over many rotations showed almost no periodic brightness variation. The light curve remained remarkably stable, with only low amplitude fluctuations, suggesting either a nearly spheroidal shape or a rotation axis aligned in such a way that cross-section changes were minimal from Earth's perspective. Such photometric stability is analogous to watching a slowly spinning sphere with nearly uniform surface tone under steady lighting, its brightness changing so slightly that only sensitive instruments register the modulation. Infrared observations across the approach and departure arcs allowed reconstruction of how quickly the object's surface temperature responded to changing solar flux. From this, thermal inertia was derived, quantifying the resistance of the surface material to temperature change. 3iATLAS showed a high value, indicating a dense, compact material with low porosity and minimal insulating regolith, much like a solid metal ingot that remains cool for a long time when brought from a cold environment into a warm room, and warms only slowly despite the new conditions. Spectroscopy across visible and infrared bands remained central. By fitting the observed absorption features with laboratory spectra of minerals and glasses, teams concluded that the bulk composition involves silicate structures and metallic inclusions that formed in environments enriched with heavy elements from earlier generations of stars. The spectral behavior lacked the broad water ice signatures typical of many comets, and instead displayed narrower, deeper features associated with high-temperature condensates, resembling a laboratory spectrum of cooled droplets from a metal-rich vapor plume rather than a frozen mixture of simple ices. From astrometry, the full three-dimensional path of the object was reconstructed. Incoming velocity relative to the Sun, angle of approach with respect to the ecliptic, and outbound direction were all calculated with high precision. The trajectory details showed that 3iATLAS entered the solar system from a direction offset from the galactic plane, at a speed consistent with typical stellar neighborhood dispersions, then passed within the outer planetary region before exiting on a different bearing. Like a precise scattering experiment in which a projectile passes near a massive central body, its path bent by a calculable angle that records the exact gravitational encounter. With the dataset assembled, three separate contradictions stood out when standard models were applied. The first was temporal. Mineral ages implied by isotopic and spectral proxies pointed to formation epochs before the Sun's birth, yet the object traversed the present solar system under current gravitational architecture. There was no inconsistency in the physics, but there was an incongruity between the age encoded in its lattice and the environment now shaping its motion. The second lane composition. Comparisons with Oumuamua and Borisov highlighted this. Borisov behaved like an ordinary comet from another system, rich in volatiles, with a coma and tail that matched known cometary chemistry within tolerances. Oumuamua showed an elongated shape and non-gravitational acceleration consistent with outgassing or other surface processes, with spectra that could still be reconciled with moderately processed ice-rich material. 3iATLAS, by contrast, presented a dry, refractory, metal-enriched spectrum with minimal volatiles, representing a class of interstellar debris more akin to unmantled planetary building blocks than to comets. The third, and most challenging, was an energy budget mismatch. Given its inferred composition and measured albedo, models predicted a certain equilibrium temperature curve along its trajectory. Infrared observations showed a systematically different temperature evolution, particularly during the outbound leg, where the surface remains slightly warmer than expected for a purely passively heated body of its size and reflectivity. The discrepancy was small but persistent across instruments. Accounting for it required adjustments to assumptions about internal conductivity, layering, and potential residual radiogenic heat, similar to a thermal experiment in which a sample cools more slowly than the textbook calculation predicts, implying hidden structure or internal energy sources that must be quantified. On top of these broad conflicts, finer-scale anomalies appeared. High-resolution spectra revealed a microspectral gap, a narrow wavelength band where absorption was weaker than any simple mixture model predicted, indicating either a minor phase or grain size distribution not yet fully matched in laboratory libraries. Sub-millimeter observations suggested a slight sub-millimeter reflectance shift compared with the visible and near-infrared behavior, hinting at surface textures or coatings that altered scattering at longer wavelengths. Thermal data contained a measurable thermal microlag, a small but consistent delay between changes in incident solar flux and corresponding changes in emitted infrared power. Together, these measurements did not require new physics. They demanded only more detailed modeling of material properties and formation environments. The contradictions were between oversimplified histories and the precise record that this body carried. 3iATLAS stood as a dense empirical sample of matter that formed in a star-forming region preceding the Sun, ejected from its original system by gravitational interactions, processed in interstellar space, and then briefly illuminated within the present solar system. It linked the earlier generations of stars that seeded the galaxy with heavy elements to the current planetary system in which those elements condensed again. After perihelion, the geometry changed. The Sun's pull lost strength with distance. The object's hyperbolic speed leveled toward its asymptotic value. Instruments adjusted exposure times upward to track a steadily dimming point. The data flow tapered. Visible light photometry captured the gradual fade as 3iATLAS receded beyond the reach of mid-sized telescopes. Infrared detectors recorded the cooling of its surface as solar flux declined, the thermal emission curve sliding downward in step with the inverse square of distance. No new features emerged. There were no sudden flares, no detectable outgassing events. Only the expected reduction in signal as the object moved outward along its calculated path. Ephemerides extended years into the future, mapping its position against the starfield. The trajectory, once a set of uncertain candidate orbits, had become a single narrow corridor through space, defined by the accumulated astrometric record. In that corridor, 3iATLAS advanced without measurable deviation, a compact vector carrying an ancient mineral record away from the Sun. Eventually, only the largest instruments could still separate it from background noise. Then, for practical purposes, it slipped below the threshold of detection. The object remained, but the observations ended. The outbound motion continued under the same gravity that had drawn it in, and bent its course. The minerals that formed before the Sun cooled further in the outer dark. The surface fractures, the metallic inclusions, the high-temperature condensates, all persisted in silence. One last solution of its position and velocity fixed its escape into the catalog. From that state, its future positions could be computed, even if no photon from its surface would ever be collected again. A final vector extended from the solar system into interstellar space, defined not by speculation, but by the measured numbers of mass, distance, and motion. That is 3iATLAS. Radiant, empirical, still.